Okay, let me talk about the all-optical probe of magnetization dynamics in synthetic antiferromagnet. My name is Shigemi Mizukami from Tohoku University, Japan. So this talk is related to the antiferromagnetic spintronics or magnonics. So you know this antiferromagnetic issue is very hot topic recently. Interesting material is this kind of bulk antiferromagnet. It's something like a nickel or iron or something. And another interesting material is synthetic antiferromagnet. That's basically consists of this film layer structure and magnetic layer coupled each other via the RKKY interaction. So my talk is related to this synthetic antiferromagnet. So recently there are many work on easy plane soft magnonics because this is interesting. So one of the example is a strong and switchable non-reciprocity discussed by this paper. So this is traditional interest in the traditional magnonics. And other paper discussed parity-controlled excitation by spin-orbit torque and also tunable magnon-magnon coupling. This magnon-magnon coupling is related to the quantum hybrid magnonics. So please see the difference shown here. By this way, the various kind of the study currently performed. However, to my understanding, nonlinear dynamics in the SAF are not well explored. So that's why we have interest on this topic. So in case of the ferromagnet, there are many work on nonlinear process in the past to up to now. And one of the example is the three magnon splitting, for example. So this is a cartoon of the frequency spectrum for magnetostatic magnon. And if we have a magnon state here, and if the magnon number population is enough large, then this magnon split to the two magnon. So this is something like amplification. And this nonlinear effect can be used for some application. For example, phase-sensitive amplifier for magnon current or generator of coherent magnon. And more recently, there are discussion of the magnon squeezing state using this kind of nonlinear effect. So this is interesting, but our question is what is the counterpart in the antiferromagnet? So in the early days, these are kind of the antiferromagnetic bulk with easy plane anisotropy. For example, hematite have easy plane anisotropy if this temperature is above the Morin point. In this case, due to the Jardinsky-Moria interaction, this canted state is stable magnetic phase. So in this case, we have a two mode. One is antiferromagnetic like magnon mode, and another is ferromagnetic like magnon mode. And in this case, net magnetization oscillates linearly because the sublattice magnetization 1 and 2 have out of phase precession. And this case, the sublattice magnetization for 1 and 2 shows in phase precession. That's why the magnetization shows this kind of circularly polarized precession. So this is correspond to the usual ferromagnetic like magnon. So our interest how this magnon interact this ferromagnetic like magnon at nonlinear dynamics. So such a nonlinear process and the bulk state is discussed in the past. This is one of the example of the experimental data, frequency and the magnetic field here. And this is the ferromagnetic like magnon, and this is the antiferromagnetic like magnon in case of nickel fluoride. And some theory indicated that there are many nonlinear processes. So among them, we can see that this process described by this diagram correspond to the swing magnon process in the ferromagnetic material. So this is just a cartoon. So if we have many population of antiferromagnetic like magnon in this kind of material, I mean this kind of magnon here, and then if the population is large enough, this magnon splitting occurred. So I mean the antiferromagnetic magnon change to ferromagnetic like magnon by the nonlinear interaction. So this is the aim in this study. So in our case, we use the SAF because SAF is very, very similar to the such bulk antiferromagnet with easy plane anisotropy. Instead of Jaruzelski-Morier interaction, we apply the magnetic field here. Then we have this candidate state. So in this case, the magnon frequency shows this way. So this is optical mode magnon. Optical mode correspond to the antiferromagnetic magnon mode here, and this decrease with field, but this ferromagnetic like magnon corresponding to this cartoon shows a linear increase. Okay, so we have a chance to see the nonlinear interaction and amplification due to swing magnon process in this easy plane SAF. So let me move on the experimental part. So in our case, we use the time-resolved magneto-optical Kerr effect based on the pump-probe technique. So we can basically change magnetic field strength and magnetic field angle and magnon precision induced by pump pulse and detected by the probe pulse due to the magneto-optical Kerr effect. And the observed signal is corresponding to the Z component of the SAF. And this is the stack and typical magnetization curve. Okay. So before going further, I just briefly mentioned how to excite the magnon precision. So this is just a cartoon for the case and in-plane magnetized film. So this is very famous paper. So so in this case, we use the pulse laser heating. So if we apply the field slightly tilt from the hard axis, then pulse heating excites the magnetization precision magnon. So this is just a single ferromagnetic layer case. But in case of the SAF, we have to think the two cases. The one is similar to the previous one. So torque due to ultra-fast demagnetization. So now we have two sublattices corresponding to the SAF, one layer or a second layer. So in this case, we can get torque which excite the acoustic magnon mode. So this is corresponding to the ferromagnetic magnon. So as same as before, the ultra-fast demagnetization induced by the pulse laser heating excites ferromagnetic like magnon. On the other hand, we also have torque due to the reduction of the RKKY interaction due to the laser heating. So as seen here, the exchange interaction coming from the RKKY coupling is sometimes sensitive to the temperature. So if we have a candidate state and the pulse laser irradiation happen, then this change of the RKKY interaction induced this kind of torque. So that's why this effect only excites the antiferromagnetic like magnon in this case. So in the experiment, we have both effects, so we can both excite two mode, and we can observe the two mode simultaneously. And this is a result with different field strengths. So in this case, we apply the field roughly 10 degrees from the film normal, and this is the signal. And this slow oscillation corresponds to the AC mode, low frequency ferromagnetic like magnon mode. And here, first high frequency mode is corresponding to the OP mode. So as I mentioned before, so we observed the Z component of the oscillation. So this Z component have both a signal coming from the OP mode and AC mode. So it's easy to extract the two frequency from this raw data. So this is OP mode and AC mode. That's why we can extract the frequency of the OP mode and the AC mode. So this is very nice technique using all-optical pump probe method. And one important point is damping in the substructure. So usually the damping is coming from the Gilbert damping, but in case of the SAF, we have a metric spacer. That's why we have to think about spin current emission due to the spin precession, the spin pumping effect. So this is inverse lifetime observed in the time result measurement for this AC mode and the OP mode. And the AC mode is basically consistent with the calculation using the Gilbert damping. So actually the AC mode totally determine the Gilbert damping. So in the AC mode, we have an in-phase precession here. That's why the spin current emission and absorption has no influence to the relaxation effect. On the other hand, this OP mode, we have out-of-phase oscillation for both mode, both layer. So spin current emit and absorbed, but this case, the magnetization precession phase are different. That's why the spin current is totally absorbed and no backflow occur. So that's why the damping is enhanced compared with the AC mode due to the spin pumping effect. So this scenario is very consistent with the early publication. If you have an interest, please see this paper. Okay, so let me move on the main topic, the nonlinear experiment in the SAF. So in this case, we measure same sample, but measurement configuration are a bit different. And so in this case, we fixed field strength here, and then the field angle different, varied from the normal to the infrared direction. So this is the data measured at the low pump laser power. So experimental data is quite nice agreement with the theoretical curve, and we noticed here some angle. The frequency for OP mode is roughly double of the frequency of AC mode. So we define this angle as critical angle. At this angle, so this condition is satisfied. So if the amplification or nonlinear effect happen, then we should see some signature of the amplification or magnon splitting process here. So this is a time resolved data. So as I discussed before, we can clearly see the precession motion. so corresponding to the AC mode and OP mode overlapped with increasing the pump laser power. So this is corrected at the angle theta B larger than critical angle. So there are the data very trivial, so signal just decay with time. This data also measured at the angle lower than critical angle, so we can get a similar trend. But if we set the angle roughly same as this critical angle, then the signal drastically change. So in the low laser power region, so signal are slightly different from others, and the high power case drastically different behavior observed. So actually the amplitude of the oscillation first increase, then decrease. So this is quite different from the other case. So we believe this is a signature of the amplification of the magnon. Okay. To see more clearly the data, we just performed the FFT, and this FFT spectra correspond to the previous one, so with different laser power. So at the low laser power case, we can clearly and see the OP mode branch and the AC mode branch here as a function of the field angle. But if we increase the laser power, then this at some point the intensity of the FFT for AC mode largely enhanced here. So this is very nice experimental data demonstrating the amplification. So to understand this effect, we again go back to this theoretical model proposed by the Professor Bauer's group. So to describe the dynamics, we use the two kinds of vector. One is Kittel vector corresponding to the ferromagnetic order, and another is a Néel vector corresponding to the antiferromagnetic order in the surf. Then after the lengthy manipulation of the mathematical macrospin equation, finally we come to these coupled equation of M and N for modeling of the surf. And this is very complicated equation, but we still see some nonlinear coupling between them, for example, here and here. So I don't want to discuss the detail of this equation here, so I just use simulation based on this equation. And this is the result of the simulation. This slit and open symbol correspond to the experimental intensity of the Fourier transform for AC mode and the OP mode. And the low frequency and this is a low power case and with different power. So this is a high power case. So as you can see here, the slit curve corresponding to the theoretical simulation result will agree with the experimental data. So that's why the modeling is quite nice and correctly predict this amplification process. In addition to this amplification phenomena, we also think about threshold for this amplification. So again, this is experimental data with different power, and this is a theoretical simulation based on that model. And actually, this signal almost corresponds to the AC mode ferromagnetic-like magnon. So as we can see here, the amplification similar to the experimental data. So I would like to say about why the amplification only observed around here. So to understand this, we just show only the signal only for the optical mode. So optical mode is heavily damped compared with this acoustic mode because of the spin pumping effect. So if here we assume the threshold around here, then OP mode amplitude beyond overcome this threshold at some time interval. So at this some time interval, this amplification happen. So point is the relationship between this amplitude of the OP mode and this threshold value. So we have to understand what determines the threshold. So this is also important for the practical application. And after the long, lengthy manipulation of the mathematical equation, finally we come to very, very approximated condition. This is the equation to determine the threshold. So if this OP mode amplitude divided by magnetization count is over the damping constant, then amplification start. So in other words, this determines the how system go to negative damping regime. So this is very interesting because if we can increase this OP mode amplitude, we can easily go to the nonlinear regime. So this can be used for some application, for example, amplifier or generator and some devices. So one possibility is the excitation of this OP mode by using the spin orbit torque. Maybe this is possible. And low damping constant is necessary. That's maybe depending on this magnitude. So if we can prepare some devices, then we can expect this kind of amplification in some electric Magnum device or something like that. Okay. So I still have a few minutes, so I wanna briefly discuss the other topic. So this is photon-spin induced dynamics. So we also work on the helicity-dependent circularly polarized light excited dynamics, Magnum dynamics. And this is just an example for how this circularly polarized light excites the spin precession or Magnum. This is just a heavy element platinum capping on the iron cobalt layer. So in this case, the light spin converted to the electron spin in the platinum, then spin precession induced by the spin torque via this interface. So this is observed data with different helicity, and basically we can manipulate the initial phase of the Magnum by using the optical helicity, photon spin. So our interest is how we can utilize this effect onto the synthetic antiferromagnet. So that's why this is just a preliminary result. So now we are focusing on this kind of the synthetic ferromagnet, antiferromagnet, capped and buffered by platinum layer. So this is very symmetric structure, and we can observe the helicity dependent signal. So we just demonstrated this one of the Magnum mode in SAF can be excited by photon spin, and this is frequency as a function of the field. This data shows something like linear behavior. So this is corresponding to the ferromagnetic like Magnum mode for this structure. So this is very, very trivial because this is very, very symmetric structure. So one of the interesting issue is to how we can manipulate the antiferromagnetic Magnum mode here by using the photon spin. This is future work. Okay, let me summarize my talk. So this work mostly done by the previous student Kamimaki-san, And collaborator is Suzuki-san and Ihama-san. And outside, Taniguchi-san in AIST and Yoshinaga-san in Tohoku University. So let me summarize my talk, and this is take-home message. So I discussed in easy plane surf all-optical pump-probe method for detection of the ferromagnetic and antiferromagnetic-like magnon. And we demonstrated the ferromagnetic-like magnon mode amplification due to the nonlinear interaction of the antiferromagnetic-like magnon. So I finally discussed the helicity-dependent photon-spin induced ferromagnetic-like magnon mode. So if you have interest, please see these papers, and thank you for your listening.